Okay, as we begin this lesson on the power function, I wanted to start out with just kind of some data and look at what happens with it. We got an example here where we have researchers in anthropology are interested in the way urban growth affects lifestyles and stress levels. They measured the average walking speed of people living in various cities and collected the data set that's shown on the next slide. You're supposed to find a regression model, decide if it's a good model, can use it to predict, summarize what that reveals about walking speed. Let's look at the data. Here we have a set of data that shows a relationship between the population of a city and then the average walking speed of those people in the city. You can do this either way. I know the easy way is just let me go through it, but it's probably always smart for you to practice. If you want to enter this data in your calculator and run a regression on it, you can pause the video and do that. Otherwise, I'm going to move forward like you've done it. And here's what it should look like after you do that. Now, this is a little bit of a giveaway. Ideally, you see that this is the data from the table. You can see all these little points. Notice that what I have run is not a linear regression. This actually has a little bit of a, it starts off lower and then it kind of comes up and curves a little bit. We're learning that not everything has to be linear. We spent a day talking about quadratic. Sometimes data has a quadratic look to it. This actually has what we call a power look to it, a power regression. The standard form of a power regression looks kind of like this right here. Y equals A is some constant, in this case it's 2.9, times X to some power. If you look at this particular example and follow what this sort of looks like, ideally you recognize this from your toolkit as a square root function. It looks very similar to a square root function. Now, it's actually not a perfect square root function. Recall that if you were going to take the square root of something, like the square root of x, that's the equivalent of x to the 1/2 power. If you look at this form here, you've got x raised to some power. Yeah, you have a leading coefficient out in front of it, but this is x raised to a power. So if this was going to be a square root function, the power, or the b value, should equal 1/2. You can see here that b does not equal 1/2. Well, the power regressions have some variation in them, I guess. It doesn't have to be a square root function. It might be a cube root function or a fourth root function, or a power function really just has to have some number being multiplied by x to a power. It doesn't have any addition or subtraction going on after it. It's really all about x being raised to some power, and that's all there is. In reality, some of our parent graphs, like the parent graph of a quadratic, is a type of power regression. In this example, the a value in front, right here, would just have to be a 1. And the b value, which is your exponent, happens to be a 2. This is a type of power regression. There's just not much going on. There's not much shifting around. No addition, subtraction. Just got to have some x raised to a power. We're looking at this kind of like it's a square root function. Ideally, then, what you recognize is anytime you come across data that looks like it might follow some sort of a square root look to it, if it looks something like that, it's not going to be a linear. Don't run a linear regression. Don't run a quadratic regression. If it looks sort of like a square root function, you're going to run a power regression on it. And if it's really a square root, then that power would end up being a 1/2. But it might be something else. Let's talk about what this would mean then. Some of those questions on that previous slide is it a good fit? I'd say looking at the graph, yeah, that fits pretty nicely. What does it mean? What's going on? Notice that right here on the lower populations, the walking speed is a little bit lower. But as your population increases, you'll find that the walking speed starts to increase as well. In other words, if you're living like in Yoder, your walking speed is pretty slow, but as you get into more populated areas, you're in Chicago, New York, now all of a sudden you're walking faster, definitely faster. The problem, though, is since this starts to level off a little bit, you can only walk so fast before all of a sudden we have to call it running. And that's why you see this start to level off. These are just speed walkers at this point, walking as fast as they can without really running. You see a little leveling off, has that square root look to it. That's what's going on in this situation. Today we're talking about power functions and looking at the different types of ways you're going to see those. To begin with, this is that standard form. Kind of looks like it on the calculator. On the calculator they had different variables they used, but k is like a constant. It's that leading coefficient. A in this example is going to be the exponent. This is the form that you see in your textbook if you were to look. And they tell you that a and k cannot be 0. If k was 0, this whole thing would turn to 0, and you'd have y equals 0. That's just a horizontal line, not really a power function. If k were equal to 0, if a were equal to 0, that'd be this exponent right here. Recall that anything raised to the 0 power is going to equal 1. And if this was 1 times k, then you'd have just y equals k, or y equals some number. That's also a horizontal line, not really a power function. We need those to be something other than 0. Now, I spent time in class and I went to Desmos and I typed this in and we looked at what can happen as that exponent changes. And I'm just going to I can't really go into Desmos very easily on this video, so I'm going to go ahead and just show you some of the variations. If a was negative, let's say, x to the -1 or -2, that actually bumps your x to the denominator. Recall that negative exponents bump it to the denominator. It would look sort of like a rational, like a 1 over x. So it's going to look like this. But as we changed that a value, didn't let it be negative, bumped it up, maybe made it a 1/2. Well, the 1/2 starts to turn into, oops, that looks funny, starts to look like the square root. And if it was less than 1/2, it was a little bit different looking, a little steeper, but as it turned into 1/2, it got a little bit higher and got higher. And then as that 1/2 got really close to, let's say, 1, well, x to the 1 is just an x, and that actually turns linear. But as that exponent got bigger and went from 1 into a 2, then the graph started to look like a parabola, like an x squared. If it turned into a 3, it looked more like a cubic, which is steeper looking and would have a bottom half to it also. Power functions have lots of options, anywhere from a square root to a linear to a quadratic and so forth. It can do a lot of things. Again, notice all of them are working right here around the origin. There's no shifting because there's no addition or subtraction. They have a lot of variability, so that allows us to use them for a lot of different things. One of the places that we see power functions, a place that you have seen in previous classes, is doing direct variation. You probably recall direct variation looking something like y equals kx. That's what direct variation is. And then you also had like y equals k over x would have been inverse or variation. Now we're going to focus mostly on direct variation because it looks so much like a power function. A direct variation, if you look back at that previous formula where I said f of x is equal to k times x to the a, that formula on the previous slide. This is a direct variation. Notice the k value. And the x happens to have a power on it, and that's okay. It's read f of x varies directly as x to the a. And you might say something about the constant of variation equals, well, in this case, it's k. Sometimes we'll know what that number is. Let's review some of this direct variation that you've done in the past. I'm going to take this formula right here and turn it into a nice statement of variation. That's called a statement of variation. If you know what your formula is, and you should know this is the area of a circle, when you write your variation statement, go ahead and use words that you know what they mean. Like A stands for area. So I'm going to start off and say the area of a circle varies directly. Sometimes we use the word proportionally as, and you look at what the variable is here. Pi is not a variable. Pi is a constant. Pi is your k value. R is your radius, and that is the variable that has a power going to it. The area of a circle varies directly as, and it's not just the radius, it's the radius squared. Sometimes they get fancy, and instead of saying as the radius squared, instead of that they'd say as the square of the radius. Either way, not the square root, but the square of the radius. And then I like to, in parentheses, go ahead and state what the constant of variation is. You can write it. I think the book sometimes writes the constant of variation is, I'm just going to say k is, or k equals. And we said the constant of variation, that coefficient on your x, in this case, is pi. Let's try another one. Write in the statement of variation. This one, again, very similar to the previous. It has to do with a circle. It's a circumference. You'd say the circumference of a circle varies directly or proportionally as, and then we have to look at this and say, what's the variable, what's the constant? 2 is a constant, it's just a number. Pi is just a constant. There's my variable right there, the radius. This time it's not squared, it's just varies directly as the radius. And in parentheses, I'm going to state the constant of proportionality. The constant of proportionality this time is not just pi, but 2 pi. Last one. Notice on this one, I don't know what this formula really stands for. There's some letters. I'm sure it means something. I just grabbed it from the textbook. If you don't know what it represents, then you can just write the letters and you don't have to actually put the words of what they mean, like circumference and radius and such. What I do notice on this one, though, is that my variable is in the denominator. That's different. That's going to be not a direct variation. That's actually called an inverse variation. Remember I said up here that this was direct variation. This is the one, if you'll recall, is inverse variation, k over x. If your variable's in the denominator, it's inverse variation. This equation or this statement would read f, don't know what it means, so I just write f, varies inversely as d squared. And in parentheses, I don't really have much to say here. I'm just going to say k is equal to, I guess, k. It didn't give me a number, it just left it as a k. I'll just leave it as a k as well. You could just write the constant of proportionality as k. All right, so this is one part that we're going to be working on, is taking some sort of a formula and turning it into words. We call that the statement of variation. We might also go the other direction. If they give us an a statement, can we turn it into a formula? Let's try a few. Test scores vary directly with the number of hours in preparation for that test. All right, so test scores vary directly. I don't see any numbers in this. I'm just going to have to put a K for my constant of variation with the number of hours in preparation. So it's going to be K times H. That's all there is to it. I don't get really caught up. I like to use variables that mean something. Use K as a default for your constant of variation. Let's try the next one. The period of a pendulum varies directly. The period varies directly. Again, there's no numbers, so I'm just going to write a K with the square root of its length. The square root of its length. Easy enough? See if you can do the next two on your own. Pause the video. This third one here, the density is inversely proportional. When you see that word inversely, that tells you to bump it to the denominator. Inversely proportional to the volume. Volume will have to be in the denominator. My constant of variation is in the numerator. I just put a K. The fourth one. This one was the tricky one because I got different stuff going on. I've got some direct proportionality, but I also have some inversely proportionality. All of that tied into, I can't write two different equations. It all has to fit into the same equation. That's all right, we can do it. Force is directly proportional. I'm going to have a K times something. Directly proportional to the mass. K times M. But it's inversely proportional. So that means I've got to have a denominator in here to the square of the radius. The square of the radius. Not the square root, the square of the radius. There you go. It's got direct variation going on here, shown here, but it's also got this inverse variation going on here. Last thing, where we can use this direct variation relationship to solve some sort of problems. Now, we're probably going to keep it pretty generic for right now. This problem says determine the constant of proportionality. That's the K. Determine the constant. I'm looking for K. If x is inversely proportional to the square of y, when y is 7 and x is 3, then write the mathematical model. That's going to be like the equation. And use your model to find x. We have 3 parts. I've underlined all the things that I'm looking for in this problem. I have to begin by finding the constant of proportionality. I need to know what k equals so that I could write my equation. X, looking right here, this is what leads me into my equation. X is inversely proportional to the square of y. That's it right there. X is inversely proportional to the square of y. That's your formula. Now let's use it to determine the constant of proportionality. Let's find k. They gave me the y is 7 when x is 3. Let's plug those numbers in. 3 is equal to k over 7 squared. 7 squared is 49. I'm just going to take both sides times 49. $50 times 3 would be 150, so 49 times 3 is 147. There's step 1. I found the constant of proportionality. Step 2 is to write the mathematical model. Well, that's pretty easy. If I already kind of have the model and now I know k, I just take k and put it in. And then that's your official model. x equals 147 over y squared. That's step 2. Step 3 says to use that model to find x when y is 13. Step 3, find x when y is 13. So x equals 147 divided by 169. In all honesty, I would probably just as soon have that as a decimal. Sorry, I don't have a calculator with me at this exact moment, so I'm going to leave it to you to go ahead and divide that out, get a decimal on it. There's your step 3. All 3 parts. Find the constant, write the model, use the model. All right, hopefully this one's a little quicker for you. Good luck.